Myself, Dr. Nitin Gramopadhye, working as Assistant Professor in Department of Humanities and Sciences. Today we are going to learn a topic, phase rule. This is what the learning outcome for the today's session. At the end of this session, students will be able to describe two component system and applications of phase rule. This is what the content we have decided to cover in this particular session. Introduction, phase rule equation, and then the reduced phase rule equation, particularly for the two component system, and then we'll apply the reduced phase rule equation for two component system, and then we'll see the applications of phase rule. This is what the introduction. The behavior of heterogeneous system with respect to changes in pressure, temperature and concentration was first studied by an American physicist, Willard Gibbs, in 1874, which is also known as Gibbs phase rule. Therefore, the phase rule is an important generalization dealing with the behavior of heterogeneous system. The phase rule describes the possible number of degrees of freedom in an enclosed system at equilibrium in terms of the number of separate phases and the number of chemical constituents in the system. This is known as the phase rule equation. F is equal to C minus P plus 2, where F indicates the number of degree of freedom, C indicates the number of components from a given system, and P indicates the number of phases which are present in a given system. Now we'll see the two component system. What is the meaning of that two component system? When two components constitute the smallest number by which the composition of each phase can be expressed is known as a two component system. Consider an equilibrium state of two component system having 0 degree of freedom. So first of all, in a previous video we observed what is the meaning of phase, what is the meaning of component. Now this is the particular example where a system consists of two different components, and therefore now what we are considering, consider an equilibrium state of two component system having 0 degree of freedom. So in a given phase rule equation, which is F is equal to C minus P plus 2, we'll keep the value of degree of freedom 0, then we'll get P is equal to 4 by putting F is equal to 0. What is the meaning of this? Whenever for a two component system the degrees of freedom is minimum, we are getting the maximum phases. That is what the meaning. Then we'll see the second possibility. When the phases are minimum, the value of degree of freedom will be maximum. According to phase rule equation, the maximum degree of freedom in two component system will be 3, and hence by putting the value of degree of freedom 3 in a phase rule equation, we are getting the value of P is equal to 1, and therefore the reduced phase rule equation is obtained for a particular two component system. Why? Because in usual practice, any two variables are selected, assuming third to be constant. In a phase rule diagram, two component system, three types of curves are expected. For example, pressure and temperature graph by considering composition constant. Second, pressure and composition graph by considering temperature factor as a constant. And the third variety, temperature and composition graph, where pressure is assumed to be a constant. Hence, the reduced phase rule equation becomes F is equal to C minus P plus 1 instead of plus 2. Plus 2 is applicable for one component system and plus 1 is applicable for two component system. Now, particularly we'll see the example lead silver system. Here, the two metals, lead and silver, are completely miscible in the molten state and they form a homogeneous state. The equilibrium diagram of lead silver system is as shown in below figure. This is the figure particularly for a two component system with an example silver lead system. Here we can see that on one axis the temperature values we have taken, and on second axis we have taken the values of composition. So here the third parameter, pressure, we are assumed to be a constant. So the phase diagram is in between composition versus temperature. This is the detailed diagram for the two component system, particularly for silver lead system. Now the phases which we are getting in a two component system, silver lead, are 4. One is solid silver area, second one is solid lead area, and third phase which consists of the molten solution of both metal, where the two metals are existing in a molten condition, therefore it form a homogeneous phase, and the last phase we are getting as a vapor phase. The vapor phase is practically absent as the boiling point of lead and silver is too much high. In such case, the pressure cannot have an impact on the system. Hence, the remaining variables are considered: temperature and concentration. Now, what are the features of this particular phase diagram? It consists of two curves, curve AC and curve BC. It consists of three areas: the area above ACB, the area below AC and BC, and one eutectic point named as a C, where all the phases are in equilibrium with each other. The curve AC, the point A represents freezing point or freezing point of the silver, which is 961 degrees Celsius, and the curve AC shows that the addition of lead lowers the melting point. The phases in equilibrium along AC are solid silver and solution of both. So whatever the curve AC is there, it is in equilibrium with solid silver and solution of both. That means two phases are in equilibrium across the curve AC. By putting the value of P is equal to 2 in a reduced phase rule equation, we are getting the degree of freedom 1. It means that the curve across the curve AC, the degree of freedom is 1. Only one variable can be defined. Similarly, the curve BC is there. It is also the second curve. The point B represents the melting point of the solid lead, and the curve BC shows that the melting point is lowered by addition of silver, and hence the conditions are also same as that of AC to the curve BC. Therefore, the value of the degree of freedom for this curve is also 1. Then we'll see first of all the areas. What the areas are there? One area is the area above curves AC and BC. In this area, silver and lead are present in homogeneous liquid form. Thus, there is only one phase. And by applying P is equal to 1 in a phase rule equation, we are getting the degree of freedom F is equal to 2. So just now we have observed for curve, the value of F is 1. But for area, the value of F is equal to 2, because for the particular area, only one phase is exists, that is a molten solution. This is for another area. In this area, solid lead is in equilibrium with the liquid of both. So what happened? By putting the value of P is equal to 2, we are getting here the degree of freedom 1. This is one more area, area ACD. In this area, solid silver is in equilibrium with the molten solution. Again, in this area also, the value of F is 1. And then we'll now see the eutectic point after observing the curves and areas. Now this is the point where all the phases are in equilibrium with each other. For example, curve AC and curve AC is a freezing point of A which falls or which decreases by addition of B to A. Thus, along this curve, the solid is in equilibrium with the liquid solution. Curve BC is a melting or freezing point of B. The point B shows it decreases by addition of the A across the curve. Therefore, whenever all the phases are in equilibrium at one point, so value of P goes to 3. How it goes to 3? One is solid silver, second one is a solid lead, and third phase is the solution of both. Therefore, at this point, the maximum number of phases is 3. By putting the value of P is equal to 3, we are getting the F value 0. That means at a particular point, if we are expecting all the phases should be in equilibrium with each other, the degree of freedom becomes 0. So all that I have prepared by referring a textbook of engineering chemistry written by Jain and Jain. Thank you.